All right, so this is round 645. Times H. Oh, for the first one, I guess. Yeah. quantity of different amounts. Sums of elements. So just the area of the rectangle? Plus 1 maybe? Yeah, okay, so what do we have here? Only stupid stuff. Over 1, down 2. 1. n months in a year, different number of days. Yeah, okay. Solid, but a little bit annoying. Yeah, so it's like, what's the maximum thing of length 2 in that window? So, I mean, I guess you probably want to end at the end of a month, right? Like if you have would there be any reason not to end at the end of a month? Move it over 1. Like it increases. If you move it over 1, the left will increase by most 1. And the right will decrease by a bunch. Maybe you don't want to end at the end of a month, though. Like if you have a 5, 1, 2, 3, 4. Or maybe you have a 7. 7, 1, 2, 3, 4. Well, 7 and some stuff in the middle. You wouldn't want to end at the 5. So what does it look like when you have a continuous range where a month doesn't start or end? That. And then, I don't know, like that. So if you're looking at this range here, if you move it right 1, then you get whichever one's bigger, I guess. But one of them is always going to be bigger than the other one? Alright, so I'm not doing too bad. Not doing too bad. Reminds me of a problem from UCF locals a little bit. I guess this is a simpler version of it though. So you have something that looks like this. You want the maximum. Yeah, you want the maximum sum. So maybe you do always end at the end of a month. I think you do, because if you move this over, all of these intersection points like if we're here, if we move right, this is what we lose. I guess we lose more than we gain, huh? Yeah, so okay, so we always want to end at the end of a month. So now we need just cumulative sums, which we can do with a tree set. X is less than a year, that's convenient. Okay. So tree set and prefix sum, I guess. Alright, nice and easy. so then this doesn't need to be a set, we have to be a map. Integer to long. Alright, so we run twice. Does that matter? I don't think this matters. Okay. Alright, so floor key. Okay, so that should let us evaluate at a time. So then time minus window size. Yeah. I think that should be fine, but like there are a lot of things I could have done wrong, so I think I'm gonna wait for it. All right, let's solve set then. Are you fired? I hope not. Okay. Oh, 0, 3, and 5. Okay. Unfortunately, if at least one total income is not a profit, directors will get angry and he will blah blah blah. Find any such K. Report that it is impossible. Can we not just pick N all the time? Oh, we also have this constraint. Why can we not just pick N? Find any such K. Oh, I guess if you had like -4, 5, -4, for instance. Yeah, so I guess -4, 5, -4 is a good example. Well, alright, so let's say the second half is all positive, right? The second half is all positive. Like the only reason -4, 5, and the -4 works is because you can count the positive more than you count the negatives. Like the positive is like comparatively more important, I guess, or like you can count it multiple times, but you can't count the negatives multiple times. But if the end of it is positive, like if the last half is positive, oh man, can this overflow? Yeah, I don't think it can overflow. Should just be product of two numbers, right? Yeah, okay, we're fine. So if the last number is positive, just try the whole thing. If the whole thing doesn't work, it's not going to work. I guess that's also true if the last number is 0. Because whatever reason we would have for not picking the entire array wouldn't hold. So now we know the end is negative. And we have no samples where that's the case. Brilliant. Why would they do that? Isn't that like the one helpful sample? Are there a lot of like wrong answers on this? Why would they not give us those? Not many. Okay. Guess this is kind of tricky. It's not always just include the middle one, right? So you've got like some limiting factor here. Can't be larger than that. And then you also have a limiting factor here. I guess, yeah, each of these prefix sums would give you some limiting factor. So you have a bunch of limits. Just take the most constrictive of all of them. Is that guaranteed to work? Well, it's got to be over half. But if it is over half, it'll work. Okay. Yeah, that's easy. We can do that. What am I doing? greater than or equal to 0, then CS n is greater than 0. And as dumb as it is now, or as easy as it is now, I think I've just finished samples. No. Ah, we do have a good... Neat. Okay, cool. All right, so then... Now it's a real case, so then we need to make a bunch of constraints. Yeah. Yes, why not just take the shortest, huh? Right? So if it's 4, then we need a length of 3. Oh wait, that's not true. Yeah, okay, we can't do this. So if it's negative, oh wait, less than or equal to 0, huh? That's annoying. What if it's 0? If it's 0, we want to take the whole thing. Yeah, I think that's still fine. Okay. So, yeah. So if the cur length is less than equal to number 2, so if it's 3 over 2 is 1. It's less than or equal to 1, it's broken. If it's 2, it's less than or equal to 1, it's broken. I don't know, I guess let's just run samples. Or sample. Oh, 6. Should be 3. Okay. Should be 4. Make it 5. It should also be 4. All right. That is very annoying. Man. Not a fan. Okay. Especially because everybody else is getting it. Wrong answer, huh? So why would it be wrong? It's either wrong because I'm printing a negative number. Let's just look through it first. So that's a thing. Well, zero gives length restriction 3. Why is that? be 4. Should be 1. Should be 2, I guess. 3. Is it 3? This is 3. This should be 2. Ugh. Looks better. All right. Not bad. Had weak samples, so I don't really, not too worried. UCF is kind of joking though. It's a little embarrassing. Saba, Magnuson are the only ones with 3 problems. Oh well. Man, prefix sums have just been the name of this game, this contest. Like, every problem, it feels like. None of the numbers are negative. That sounds like a red herring. Like, that's definitely a red herring. Because all numbers are positive, right? And each time... Oh, wait, I guess... Yeah, no, surely that's a red herring. Because all numbers are positive, and each time you use it, the sum of everything double. Well, is it? Wait, what? What does this have to do with cookies? Alright. Solve this problem and get the cookie, or the coronavirus will extend quarantine for 5 years and make the whole economy collapse. That's unfortunate. minimum number of operations of the second type exceeds this giant number. But like that's the only time this will ever happen, I think. Or maybe not. Yeah. If your array is over length 2, that can't happen. No, it can happen. Your array could be length 3. It could happen. I think. 1, 2. Increased by 2, I guess. 3, 1, 3. Yeah. Yeah, so your array can be length 2 or length 3. But if it's length 4, then that won't happen. What does R mean? Reverse and replace. P is replace. Oh yeah, so you make it 1, 13, and then 13, 1, and then 13, 14. So the final array has to either be increasing or decreasing if you ever use a cumulative sum array. So that cuts down. Like, that's an important restriction, for sure. And also, it's always small if the length of the array is 4 or more. Because if it's 4, then this first thing increases linearly, the second thing is quadratic, the third thing is cubic, and the cube root, or is it even cubic, or is it, I guess it's cubic, yeah. It increases by a quadratic every time, so it's cubic. Yeah, so then the cube root of 10 to the 12th is small. So we have to handle the small cases and also the general case. How do we do that? All right, so if n equals 1, then you can't do anything. Right? Yeah, okay. So then what if n equals 2? If n equals 2, oh man, this is one of those annoying a plus equals b things. God, I hate these. They're the worst. Right? You can add either number to the other number. Man. I've seen this problem before, and I've put a lot of thought into it, and I haven't gotten anywhere. It's like, so the problem is you have two numbers, A and B, and you have to get them to reach like C and D. And your two operations are A plus equals B and B plus equals A. And the question is like, I think the original question was just, can you do it? I guess here you have to extract how to do it. But that's like exactly this problem with a constraint that n equals 2. So like an easier version of this problem even. I guess it's just a more general version of this problem though. Maybe? I don't know. Maybe not. Maybe what happens in the middle is a bit more complicated. Man. This is an annoying problem. Who solved this? This is very annoying. Okay, so you've got A and B. Need to get them equal to like C and D. Man, I've seen this problem like several times before. I should definitely know how to do it. Well, I don't know what's code forces, right? So we have Google. called? I think it was a Polish problem. Well, I guess I shouldn't dwell on it too much because even if I had that solution, I would still need to make it work for like 3, for n equals 3. Here's the real question. Are there multiple ways of solving it for n equals 2? Because what it feels like is the first and last elements, like there's a forced number, there's a forced set of operations you can do in order to solve those. And then I guess you just check for everything else if you do those operations. What does it look like? Which might be a bit tricky to simulate. No, it shouldn't be that bad because you can't switch left and right more than like log times, I think. Yeah. And if you go left twice, it's relatively predictable. Or is it predictable? It should be. It's more predictable than switching at least. Oh no, yeah, it's easy because if your array is really long, like if your array is 10 long, then the last element grows at the power of like, or in the order of like n to the 10th. So if your array is 10 long, then you only do 10 moves max. Yeah, so it seems like if you can solve this for n equals 2 and for n equals 3, it should be very easy to solve for every other case. So how do I solve it for n equals 2 and n equals 3? So I need to end up where I can repeatedly add A in order to finish. And then I need to get to some place where I can repeatedly add A by repeatedly adding B. And I need to get some B that I can add by adding an A to it several times. But then when stop guaranteeing things. Suck at math, man. I don't even know where to go. Like, I don't know. I don't see what to do here. Alright, what if we brute force which thing results in which one? I mean, I guess that doesn't really help, but so A has to get to C, B has to get to D. So it'd be nice if we could end with like 7. 7 to 5. Yeah, 7 to 5 would be nice. And then 2 5. In order to get to 2 5, we could do 3, 5 or 1, 5 or 1, 2. Oh, so is this like Euclidean's algorithm or whatever? Euclid's, Euler's form, I don't know. The GCD thing. Extended Euclidean, that's the name. Yeah, if we want to get to 1, 1. All right. So I can get from 1, 1 to any pair of things, can I? Yeah, so I go 1, 1, 2, 1, 2, 5, 7, 5, 7, 12. So if the array started out as 1, 1, then I can do it? Is that right? That's kind of surprising. I don't know. Maybe it's not. I find it kind of unintuitive. I would have imagined that like this a plus equals b thing is a pretty hefty restriction, but maybe not, because I just have come up with an algorithm to do it. Okay. So what if we start with 1, 3, and now we need to get to 7, 12. Well, 7, 12 has to come from 7, 5, which has to come from 2, 5, which can come from 2, 3, but then we're in trouble. Oh, is that it? Okay. I guess I just didn't understand extended Euclidean. So then, all right, so we have to get to, like, you have to just mod whichever turn you're at by the other one, because if you don't, then, like, you couldn't have come from anywhere, really. So it's easier to go backwards, and then beyond that, you want to like just alternate modding by one to the other, and then you can go backwards at the end. How much time do I have? 20 minutes. I don't know, might be able to get it. It's probably not, but maybe. This constraint's kind of annoying. I guess it's not that bad. Yeah, okay, I think I can do this actually. Because whatever the checker is, it needs to simulate these operations. So I definitely need to be able to simulate the operations. So extended Euclidean to get how to do the outsides. And then I get my things. Oh wait, how do I do 3 though? I don't know how to do 3. Like that's n equals 2. What about n equals 3? Because for n equals 3, you have stuff in the middle that changes, which is even worse. Tricky problem. This will be a good one to read the editorial for, though, for sure. Like, this is the kind of stuff that I need to get better at. The first step you increase by 2. Then you increase last number by 3. I guess then by 4, then by 5. So it's like, I don't know, it's kind of predictable. But then when you switch sides, this one's going to be a 5 and this is a 1. So then you're increasing, man, that's like annoying. Do you know? Like, you have to know what the middle things are to know where you came from. Oh, maybe I can just do it the same way, though. So let's say I'm trying to get to 7. It's got to be increasing, right? That's the rule. 7, 12, 27. And then I'm coming from, what, I guess 1, 1, 1. So where could this have come from? Well, we would have to propagate left, surely. Oh, maybe it's just like do it. Ugh. I don't feel like it. Okay, so in order to get here, we definitely did like a left shift. So this thing came from 5. That means this thing came from 7 plus 5. This came from 15. I guess that means we went, well, then it's impossible. Yeah, it looks like it's very implementation heavy. I don't know, maybe not. It seemed like E would be very implementation heavy, but E was actually super easy to implement. So I could just be wrong. But it definitely seems like the answer is to go backwards. Like it's definitely easier to go backwards, it looks like. Try to go from B to A. Like if you have, there are no good samples, okay. So 7, maybe something slightly more common. Let's just go forwards and try and reverse engineer what we did. 1, 2, 1, 2, 1, 3, 4, 2, 1, 4, 4 plus 4 is 8. Now let's go the other way. So 8, 12, 12 plus 1 is 13. Let's go left again. Or let's go left again. So then 8, 20, 20 plus 13 is 33. Maybe we'll go left again. So 33, 53, 61. Okay. So after we're done with this, that means we know this came from 33. Oh yeah, so you can binary search how many times you do it. Or, oh wait, so n equals 3 is really just like a special case, because sometimes it's possible. Sometimes it's possible to do a huge number of operations, but sometimes it's not. But like for n equals 4, or for n equals 3, it's quadratic. Oh, you can just do n equals 3. So n equals 2 is just really annoying. Man, dude, okay. So I guess we can special case this. 1. Okay. Okay, so then how does GCD work? E0 be a 1. Sure. Finish A. E0 be a 1. Okay. Is it big? Okay. All right, so then Oh, we don't care about how many moves. Oh wait, we don't want to reverse in the beginning, we want to reverse at the end. Because otherwise we'll mix up which one is A and which one is B. Alright, well, so I'm not going to finish. Let's see how close I am though. Reverse. Add. Reverse. Like one away, right? Darn. Alright, well, I don't know. Good contest. I liked all the problems. Thought they were all pretty neat. I guess I'll go over them real quick since I didn't do much commentary in the competition. Park lighting, I don't know. I'm not really sure about this one. I just kind of like tried stuff until it worked, but it seemed like you can just, if it's like you just place it on these ones and then you place them two below. And then if it's odd by odd, there's a better way of doing it. So you just do the first row separately, and then, because like you'll waste a bunch on the bottom row, like you'll place it here and then here and then here, when these are all just covering one, so you could do better. So yeah, so that's that. That's, I don't know, not really super helpful, I think. What was this problem again? Oh yeah. Yeah, so you just like, obviously you're just going to invite as many people as you can, and then there's no reason not to invite some prefix sum of them in sorted order, like some prefix of them when they're sorted, and then you'll just like say, okay, brute force the number you're going to invite, and then say, if I invite this many, does the most particular person, the person who requires the most people there, are they satisfied? And if they're satisfied, then everyone else is satisfied, because all those people require even less. So that's pretty straightforward. Problem C was quite interesting. So one thing to notice is if you're only going down or right, then each one of these colors that they have here, that they've nicely colored for you, you're only going to hit one thing of each color once. So since we're only looking at like the differences between paths, we don't care about the absolute values. What you can do is you can replace this 2 with a 1, and this 4 with a 1, and the 7 with a 1. So it's like 1, 1, 2, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5. And when you do that, you just have 1s on the first row, 2s on the second row, 3s on the third row, 4s on the fourth row, etc. So then the question becomes like a lot easier, because like it's very easy to see when like one path is bigger than another. So yeah, the other thing you can notice is like if you're starting here and these are all 1s, like it's 1 on this row, it's like a totally symmetric problem to starting at a row below. So you can just move your rows up until they're on the top row, and then handle things like that. So then what you have is something that looks like this. So if you want the smallest total possible, that would be this path here. This would be like the smallest path you can possibly have. And then if you want to increase the size of that path by 1, then instead of taking this one here, you could take this 2 here. That would increase the path by 1. If you wanted to increase it by 2, instead of going like this around this corner, you could instead go like this. So that would increase the path length by 2. This would increase it by 3. And then if you want to increase it by 4, you could go like this. So you can easily increase it by 1. But the max that you can get is this here. So this is, the green is like the max path you can possibly make, and the red is the smallest path you can possibly make. And we want to see, all right, what's the difference in these paths? And that will be the final value. And it turns out, like, if you look at how you can increase them, each time you move over one, like each one of these right here, let me use a different color. So each one of the things I've circled in blue can correspond to adding one more to your answer. And then you also have this one original path. So it's this one path plus the size of this square. That's your answer. That's why it's like super easy to code. Yeah, so for problem D, there's a UCF locals problem that was similar to this, but basically if you draw out the graph of the number of points you get, like the value of each position, it'll look something like this. Oh no. Yeah, it'll look, I don't know, maybe something like this. So what you can do is, I don't know what to do with that. You can move everything over a little bit. So like what your window is going to be is it's going to be like maybe some range from here to here, and that's your window. So what you want to do is you want to maximize, like this is how many hugs you get. So this is time here. This is your number of hugs. And you want to get as many hugs as possible. So if you look at this window right here, then you can see this is the value at this time, and this is the value at this time. So you get more hugs on your first day than you do on your last day. So what you could do is you could move your vacation one day earlier, and if you do that, then you get more of these hugs, and then this number decreases, and this also decreases. So in other words, you would rather have this day than this day. And you can trade those by moving your range over by 1. So yeah, so we can keep doing that. And then you can see since these slopes are the same, you're always going to want to do that. And then that trade-off only stops being beneficial when you're right here. Another way of looking at it is if we take this graph and we look at like the range, the interesting points are when this intersects like the same graph but translated over by a little bit. And all of those intersections are going to happen on these vertical downstrokes since all the slopes are the same. So we need to check all these vertical downstrokes, and all of these happen at the end of months. So you know your vacation is going to want to end at the end of a month. So then it's just like cumulative sum stuff. In order to validate that. Are you fired? Okay, yeah. So this is a very cumulative sum heavy problem set. So yeah, so there were a couple observations here. The first one was that like you can case out this last half of the array. If it's positive or negative, or like 0, and if it's positive, then there's no reason, like the only reason not to have to not just like give the sum of the entire array is if you can decrease it and then count like the middle twice and count the outsides only once. Like that's why you might not want to include the entire array. And that won't happen if the income, like if your steady income at the end of the month or at the end of the period is positive, because then you'll want to include the part at the end. So there's no reason to shrink it to anything less than just the entire array. So if it's, and that happens if it's 0 too, like there's no reason not to include it. So in all of those cases, you can just try the entire array and either that works or it doesn't. The case that's left is if it's negative. So when it's negative, oh, no, don't save. When it's negative, you have like a bunch of these values here. And then at the end, you have this continuous block that's just like all the same. And then this is the middle of the array. So this would be 5 long. There are 5 things here. So what you can do is for each one of these, you know that the length that you have to take has to be at least this amount, because these are all negative. And since these are negative, like these can be positive or negative, but since these are all negative, if the amount you take is less than like n over 2, like if it's less than half, then when you get here, you're going to have to give them this number, which will be negative. So that doesn't work. So you have to include a number that's more than half. So each person that you start at, you can keep like all of these people, that's fine, or like that's required at least. And then once you do that, you're going to have to keep like some amount of this negative as well. And you can say, all right, what's like the most negative things you can keep here? So if we know that number, if we know like the maximum number of negative things that we can keep, then we'll get a bunch of like requirements for this guy. Really, it's just one requirement for him. And then if that's like just the entire array, then we're fine. But otherwise, when we get to this guy, we'll have another requirement. And that might like shrink the maximum length we're allowed to use. And then as we move left here and look at people that we might need to, that like might have to be valid left starting points, then they might shrink the array even further. So basically, as you move left here, the size of the array will shrink. And you stop as soon as like it's legal. Like you stop as soon as like the size of the array lets it, so that you never have to start here. Because like if the entire array is just like everyone minus 1, that means there are only 2 positive things you have to ensure, which are like these 2. And then you don't ever have to consider this guy. And the only reason we have to consider this guy at all is because this first guy's restriction was you can't include the entire array. You only have to include like everyone but 1. Yeah, so that makes sense. So then to figure out how many you can do here, I think you can just do math. I just did a binary search because, as you can see from problem F, I suck at math. So for problem F, I don't know, there might be a better way of doing this. My idea is if n equals 1, then the array can't change, because reversing it and doing cumulative sums doesn't change anything. If n equals 2, you are given the problem where like you have 2 integers a and b, and then you have to turn them into c and d, and your 2 operations are a plus equals b and b plus equals a. So you can do this with extended Euclidean. I'm not going to try and explain it because I'm not good at extended Euclidean. I just like kind of learned it in contest myself. So there are probably better resources for that online. So that's n equals 2. Then for n equals 3, or I guess if n is greater than or equal to 3, then you have the convenient requirement that it's not going to take more than square root n moves, because each time you do one of these sums, like you're not going to do 2 reverses in a row. So every time you do a reverse, that's followed by a sum. But anyway, each time you do a sum, you increase like the first number by 0, you increase the second number by like a constant, So this one's like +1. And then this next one, you increase by this value. So this increases linearly. And then the next one will increase by something that's increasing at a quadratic rate. So then this one will increase by n squared. So if you have 3 things and you take n moves, then this will be like your biggest thing will increase at a rate of, it'll be about n squared or bigger, which means you can't do more than 10 to the 6 moves before you pass the maximum requirement. So if you go backwards, that means you'll get below whatever you're trying to hit in 10 to the 6th moves, basically. Yeah. And then if n is bigger than 3, like if n is 3 or more, I think you can just do it. Like you don't have to do this mod stuff. When n is 2, you have to do mod stuff with like, yeah. But when n equals 3, I think you can just say, all right, where would this come from? And just like simulate it. And then like you might ask, well, this might take like 10 to the 6th moves and n might be huge. But that won't actually happen because when n is large, like when n is 3, it might take 10 to the 6th, right? But when n is 4, then it'll take cube root n, which is like 10 to the 4th. And then when n is 10, it'll only take like 10 moves because it'll be growing at about n to the 10th. So it should be very easy to just simulate. Like you shouldn't need to worry about time for anything other than, I guess, these 3 cases here. And the last thing is, how do you know which way it came from? So if you have an array, like if this is your B array, like 7, 1, 12, then you can't actually get this because anytime you run cumulative sums, it'll be increasing going this way. Or if you run cumulative sums and then reverse it, it'll be increasing going this way. So you know exactly where it came from. So like you can tell which array it came from, and you can just like step backwards until you get to the right array. The tricky part is just handling this quickly. So I think I was almost there. Like if it were a Div1 contest, I probably would have gotten it. I probably would have had enough time and maybe a little bit more discipline. Like I would have thought about it harder probably instead of checking the scoreboard. But oh well. Yeah, thank you for watching. Goodbye.